already discussed enhanced enhanced weathering as a way to sequester carbon into soil, mostly where you grind up some appropriate rocks. In a natural process is that the rainfall typically dissolves CO2, produces carbonic acid, falls on rocks and slowly weathers away the rocks and sequesters CO2 into the ocean through various processes, and that typically works on geologic timescales. It's a very slow rate, but it's been very critical in the history of Earth overall as well in terms of modulating CO2 and hence climate. Here it's getting a longer treatment in terms of a review, and they consider all the aspects, including reverse weathering in the ocean, what happens in the soil, potential acidification, pH issues, what happens in the rivers, and policy issues, funding. And honestly, right now it's small that it may take a while to become a big part of the overall carbon capture and storage process or portfolio. Or it may never happen. Nonetheless, this article is nice, so I'm going to just give it a brief treatment. It says challenges and opportunities in scaling enhanced weathering for carbon dioxide removal, CDR. Terrestrial enhanced weathering on agricultural lands is a proposed carbon dioxide removal technology involving the amendment of soils with crushed base cation-rich rocks. We'll see some reactions later, such as basalt. Over $250 million have been raised by commercial EW startups across the globe, accelerating the deployment of EW at scale. At scale, honestly, has to be gigaton these days. In this review, we outline the scientific knowledge and policy requirements for scaling EW. So, will there ever be a policy to say you must do rock enhanced weathering on your fields? Maybe. Depends on your NDCs, nationally determined contributions, and whether you see that as a significant contribution. The global CDR potential of EW is 0.5 to 2 gigaton CO2 per year by 2050, and that's the net zero timeline for the global warming target up 1.5 and 2 degrees C by 2100. Tracking carbon as it is transferred from soils, so cradle to the ocean's grave. So goes from soils to the oceans, cradle to grave, fully considering and quantifying lag times in CDR and developing a robust framework of monitoring, reporting, and verification of CDR are all important for understanding the performance of EW deployments. Monitoring, verification, reporting, MRV, reporting, verification are critical because you want to show there is, in fact, additional CO2 being taken out of the system by whatever you do in this case. And in a life cycle sense, they should, in fact, be removing net CO2. Policies aimed at incentivizing responsible deployment and gaining acceptability among directly impacted communities such as agriculture are essential to sustainable and long-term growth of EW. High initial prices, the lack of consistent methodology for issuing carbon credits, showing you actually put away extra carbon, and life cycle carbon emissions associated with the deployment are the main challenges of scaling EW through the voluntary carbon market. Future research needs to explore the co-development of EW and other CDR technologies and utilize long-term, that is greater than 10-year, instrumented EW field trials to evaluate processes that regulate CDR efficiency and agronomic and economic co-benefits. That's the main story. I'll add some details. It's obviously a review paper, long paper, lots of very nice references, but I'm going to make it relatively brief, of course, starting with a nice infographic here. Overview of enhanced weathering of crushed basalt rock on agricultural lands. Enhanced weathering involves rock extraction, transportation, and application of basalt to fields by geochemical processes in soils, inland waters, and coastal oceans. So that's the whole line of components involved, which means life cycle analysis becomes very critical. For example, being proximal to a field where you are crushing the rocks and putting them on is going to save you a lot on transportation, but can you keep on doing that forever, or does it make the soils too acidic at some point, and so on, right? Here in inset, we are looking at basalt is weathered by reaction with water and CO2, producing new minerals, silicic acid, nutrients that support plant growth, co-benefits. Bicarbonate ions, SCO3 minus, make their way to the sea, achieving long-term carbon storage. So in the ocean, you have H2O plus CO2 giving you H2CO3 in the natural dissolution process. But if you bring HCO3 minus also, you will continue that reaction, because H2CO3 goes to HCO3 minus H plus, and then HCO3 minus goes to CO3 minus minus and H plus, and CO3 minus minus can combine with calcium to form calcium carbonate for all the corals and other shelled animals, right? So here is basalt. Here is a crushing process being transported and put on the field here, where some agriculture is going on, and CO2 is flowing. So here it is being captured into crops as well. So you are seeing some emission, but more uptake. So negative CO2, so net uptake, and here HCO3 minus coming into the rivers, flowing out into the oceans, and some CO2 gets released along the way as well, because HCO3 minus can always re-release the CO2. It can go into the soils, so that HCO3 minus can become, continue with other HCO3 minus coming in, and lead to CO3 minus minus, as we mentioned, and can go to the bottom of the ocean, which is the grave that we talked about. So cradle to grave. And here is basalt, calcium, silica, magnesium, iron oxides, CO2 plus H2O, giving you FeOH3, Ca2 minus minus, so Mg2, please read them, 2 plus Ca2 plus, Mg2 plus, H4Si4, HCO3 minus. So oxides contained in basalts, shown in the gray colors, CO2 from root and microbial respiration, shown in these orangish colors. And products produced are minerals, silicic acid, nutrients, and bicarbonate in these various colors. But you get the idea that you must track everything to the from the cradle to the grave to ensure things are working the way. I jump ahead to now mechanisms of enhanced weathering. Enhanced weathering feedstocks include olivine, wollastonite, and basalt. Basalt, primarily composed of oxides of silicon, iron, aluminum, magnesium, and calcium, is most widely used, as we'll see in a table, because they're abundant, and basalt is abundant and widely distributed globally, with relatively high concentrations of plant essential nutrients, which is what you want in the end, enhance soil carbon and sequester away CO2 and make it, enhanced soil carbon has a virtuous cycle, which I always mention, makes soil erosion resistant, drought resilient, increases its capacity to hold on to nutrients, becomes less susceptible to erosion, and so on, and crop yields go up, of course. After being applied to soils, crushed basalt is weathered to produce new minerals, silicic acid, nutrients, mobile cations such as Ca2 plus and Mg, so that's Ca plus plus and Mg plus plus, and bicarbonate ions HCO3 minus. HCO3 minus, of course, experiences a series of geochemical processes that we'll see, with potential of being converted back to CO2 before reaching the sea for long-term storage, which is what we said here. Okay, weathering and carbon removal. Jumping ahead again. Weathering occurs when carbonic acid in rainwater produced from dissolution of atmospheric CO2 that I mentioned already. So H2CO3 minus removes CO2 and consuming H plus ions. The reactions we will see, again releasing base cations like calcium plus plus, magnesium plus plus into solutions. Release of base cations increases the alkalinity of the soil solution, its capacity to neutralize acid, because H2CO3 is converted to negatively charged carbon species, potentially HCO3 minus and some CO3 minus minus. Weathering products such as base cations, HCO3 minus and silicic acid are then transported through soils to rivers, subsequently to the ocean, where carbon species are securely stored away for more than 100,000 years, if they go into the deep ocean and remain unperturbed, right? If ocean keeps warming, all bets are off again. So CaSiO3 minus silicate rock typically takes 2 CO2, which is critical, as opposed to calcium carbonate, which takes 1 CO2, can re-release it. So 2 plus H2O, of course, gives you a base cation that we mentioned, 2 bicarbonates, and H2SI4. Some of the HCO3 minus ions produced via equation 1, might in some circumstances subsequently participate as carbonate minerals within the soils and rivers, which you see here. So although soil carbonate can be stable on timescales of greater than 10,000 years, in an EW setting, stability is highly dependent on water availability. Carbonate that precipitates during drier periods might redissolve when it's wet. Okay. So here is the reaction going from calcium plus 2HCO3 minus to calcium carbonate plus CO2 plus H2O. So you are releasing this and locking up 1, which is why this 2 is critical. Okay, characterizing the chemical and mineralogical composition of the mineral feedstocks before application to agricultural lands is important to understand the potential and the rate of CDR. And there are some details that I'll skip. But depending on which feedstock you use, weathering of 1 ton of olivine, which is Mg2SiO4, can remove 1.2 tons, up to 1.2 tons of CO2, whereas weathering of 1 ton of albite, which is NaAlSiO3AO8, removes less than 0.17 tons of CO2. So this is then critical as to what is being crushed and weathered and where it's coming from. So life cycle becomes very critical. Olivine is also relatively fast weathering, whereas albite weathers much more slowly at pH 5, with complete dissolution of small grains taking hundreds of years. Silicate feedstocks often contain trace quantities of secondary carbonate minerals that can weather rapidly as well, with only half the CDR potential of silicates though. So multiple details there, but I'll not go through it because we are only going to focus on whether enhanced weathering EW will ever scale up and becomes a major player in overall carbon capture, which may become inevitable for reaching net zero and the global warming targets. What happens in the soils? You have already some reactions we looked at. This one is a different one, looking at weak organic acids derived from decomposition of organic material, reducing the efficiency of CDR. So again, CaSiO3 plus 2HNO3 plus H2O, leading to Ca plus plus, 2NO3 minus, and H2SI4. Okay, so I'll just leave it there, but you have to always make sure of all the reactions involved in the cradle to grave, and any leakage or re-release that happens along the way is part of the monitoring, reporting, and verification for additionality. Okay, enhanced weathering companies, I won't read all of them, but they are across the world. So Canada, Australia, UK, Brazil, US, Ireland, etc., even India, Tanzania, and Zambia. And they are using different feedstocks: basalt, wollastonite, olivine, recycled concrete, and basalt. So if you can, recycled concrete is going to be critical because many of the buildings get broken down and rebuilt, and you produce a lot of concrete waste, and recycling that is now a big discussion as well in terms of sustainability. Capital raised there, and then there are some notes that basically gives you a sense that there are many companies, multiple in India, multiple in Brazil, many in US, good to see Mexico and Germany here as well, Kenya, Cameroon, Austria, France. So, everybody is trying this, of course. Remember, no matter how many of them try, in a life cycle sense, each one of them has to be net negative for carbon. Otherwise, you are just playing games. Tracking and measuring of carbon uptake in soils becomes critical for quantifying it. So three-phase measurements are complementary and can be used for benchmarking EW reactive transport models, development of robust and cost-effective protocols for quantifying CDR is essential to unlock financing and facilitate large-scale EW deployment, as well as making sure that they are not being used as offset by companies, offsets as paying off for their emissions, saying we did enhanced weathering somewhere without proper accounting for additionality. Downstream processes and removal efficiencies, of course, biogeochemical processes within soils and groundwaters during transport of soil waters to the ocean, and processes within the ocean can lead to transient or permanent losses of alkalinity produced via weathering, lowering CDR efficiency downstream from where weathering occurred. So we will look at the figure here in a minute. But basically, remember, we used enhanced alkalinity in the ocean, or we mentioned enhanced alkalinity in the ocean as another ocean CDR method, ocean carbon dioxide removal method, and enhanced weathering can essentially amount to enhanced alkalinity as well. But we have to make sure that alkalinity is not lost from the cradle to the grave. So here is the schematic of downstream processes that affect carbon dioxide removal efficiency without going into detail. Agriculture, of course, so there is the shallow soil activities where you are producing bicarbonate. So cation retention, carbonate formation, plant uptake, secondary mineral formation, etc. must make sure that CO3 minus stays in the deep soil and doesn't turn into CO2 leakage, as you can see here in the rivers and streams that we already mentioned. So calcite precipitation and calcium carbonate formation, there can also be degassing along the way. And groundwaters, again, microbial nitrate reduction processes. So this is a negative and this is a positive here. So soil that increases or decreases carbon dioxide removal efficiency of enhanced weathering. So you can say this here CO2 release decreases via degassing. Calcite precipitation decreases the efficiency, but microbial nitrate reduction can increase the EW efficiency. In the oceans, you can have reverse weathering processes where some locally produced clays can do reverse weathering. So if weathering is taking out CO2, reverse weathering will of course re-release the CO2. So you can have some CO2 degassing with HCO3 minus going back. So if you increase CO2 in the atmosphere, acidification is basically increasing the H2CO3 or aqueous CO2 and so on in the ocean, decreasing the pH, and it can drive a loss of CO3 minus minus through loss of HCO3 minus. So you can have acidification impacts on corals and others. Okay, so calcite precipitation, orthogenic clay formation, which is what causes reverse weathering, and eventually you have to reach the deep ocean, and the amount of export is going to be critical. So if you keep doing enhanced weathering and keep bringing via streams and rivers all these products of weathering, then how much of it actually makes it to the deep ocean for sequestration is going to be very critical. Of course, soils have many reactions. I won't go into the details, but you can see this is figure 3 here, showing various processes, and I won't go through all these chemistries, of course. This is, of course, the impact of soil cation exchange on the time dynamics of carbon removal. So how long it takes and how long it stays. You can keep it locked away in soils up, for a while if it's unperturbed, but there are many other things going on with human perturbation. Agriculture is what we mentioned here, but also enhanced respiration because of warming and loss of carbon that way as well. Okay, so here is CDR percentage wise. So this is CA exchange, and this is CDR. So as long as you are not, let's just read it, okay? A base cation such as calcium plus released from enhanced weathering feedstock are charge balanced production of charge balanced by production of bicarbonate, but some fraction of the base cations Ca++ released will replace exchangeable acidity on soil exchange sites. This release of exchangeable acidity consumes HCO3-, reversing a portion of the initial carbon removal. However, the base cation will eventually be cycled off the soil exchange complex, regaining some of the initial carbon removal. So the kind of details that may matter in the end, but when you are looking at its EW's potential as a part of the large-scale carbon sequestration, then obviously you are dealing with such details to make sure that in a life cycle sense, again, there is net removal. Okay, groundwater plays a role, of course, as we saw already, the source of organic matter for nitrate reduction that we mentioned, which can enhance EW efficiency. And it's important to understand whether a given treatment of the groundwater mobilizes an otherwise recalcitrant pool of organic matter relative to the counterfactual case. So enhanced weathering is changing the chemistry, and there is some pool of organic matter sitting there. If your enhanced weathering is going to go into groundwater and start respiring that organic matter and releasing CO2, then you may completely negate the impact of enhanced weathering on the one hand and this respiration on the other. I'm being very brief, but that's the basic point. Oceans and sediments, of course, we mentioned reverse weathering, but here coastal ocean is the final filter that carbon must make it through to be considered removed permanently, so it has to go to the deep ocean. Many of the same processes discussed earlier apply here as well. Re-equilibration of the carbonate system as fluid mix could drive CO2 degassing or uptake depending on the chemistry of the background surface ocean, and secondary clay or carbonate formation can remove base cations and reduce CDR efficiency. There are other things to consider in rivers and streams that I won't talk about. So as a review paper, they must consider all these things, and they are important for overall life cycle analysis. But we can just jump ahead and say several processes can alter solute fluxes after initial CDR in the field, but the key question is whether base cations are permanently removed during solute transport to the ocean. Permanent base cation removal should be considered a true reduction in overall CDR efficiency, and it will be important to forge better empirical and theoretical constraints on the processes driving permanent base cation removal. Transient CO2 degassing and or transient base cation removal, for example through redissolution of secondary carbonate, however, should not lead to substantive reductions in overall CDR efficiency. So overall, what is the potential? Understanding the CDR potential of EW with agriculture is important for assessing its possible role in assisting global and national net zero greenhouse gas emissions. It's most likely going to come in as part of the NDC. This is why every country is trying it. It's not to make money. It is a potential co-benefit for agricultural soils, but mostly it is to show that you are removing CO2 as per your commitments to Paris Agreement. Estimation of CDR potential and rates and the MRV of CDR via EW will largely rely on predictive modeling approaches given the likely costs of field measurements at scale. In this section, the modeling approaches and their resultant estimates are discussed in detail, which I'm going to skip, but you understand that there is no way to take an instrument and measure how much CDR is happening. You are going to rely on models that are going to be constrained by the observations so that you actually are convincing somebody that you are doing additional carbon sequestration. So there is the modeling part. Numerical modeling frameworks can be used for various purposes, including acquiring better mechanistic understanding of a discrete EW process, predicting downstream impacts, refining systems optimization at the project or regional scale, or as a cost reduction measure for supplier-based MRV on a voluntary market. So somebody is doing EW, somebody is doing MRV, and somebody is getting credit for doing additional carbon. So the whole thing has to be closed in terms of not just being a greenwash in the end, right? So it's critically important that the right framework for evaluating and validating models is established now, as large-scale field trial data are growing rapidly and might become accessible to various stakeholders. So if we looked at the table of a long list of companies doing this, there has to be a monitoring and policies and so on. This is the cradle-to-grave framework for tracking carbon flow then. The on-field monitoring, reporting, and verification. So model validation and model prediction are a loop here to make sure everything is going well. And reaction transport model is considering input of feedstock like basalt and fluid flow and what's happening in the soil from the surface to deep soil, and how the HCO3 minus is going around. So here is the catchment and river network for, let's say, the Mississippi, I think, that's going down here into the Gulf of Mexico. And HCO3 minus is going into the ocean, and you are estimating some ocean storage, and you are expecting the quantities to be, matching the gigaton scale requirements. Here it is in micromoles per kilogram in the oceans. So carbon and alkalinity can be recycled and carbon potentially released after delivery to the surface ocean before being permanently stored in the ocean interior. In other words, you must figure out how much is coming into the surface and how much is actually making it to the bottom for a longer geologic timescale sequestration. So there are estimates of CDR potential that I won't read, but here carbon dioxide removal potential of enhanced weathering on the agricultural land worldwide. Here, regions. So who is monitoring, reporting, and verifying that? You have to be careful. So these are different rates of application. So I won't go into the details, but in the first one, they're doing scenarios. 70% of cropland is using EW deployment with 10 tons per hectare per year of basalt application rate for 2006 to 2080 average. 2006 to 2080 average. And second one is using a lesser one. It's using 40 tons per hectare per year basalt application, 2020 to 2070 average. So just take it for what they are, but notice the gigaton per year numbers are relatively small, but globally they should add up to gigaton scales indeed. So here you are looking at the number we mentioned in the abstract, 0.54 to 2 total for the first scenario, and for the second scenario it's 0.52. What are the co-benefits? Applications of crushed silicate rocks to agricultural landscapes could have important implications for global food security, thus requiring rigorous environmental monitoring. This section outlines evidence of the environmental impacts and examines monitoring requirements. Okay, I won't go into the details. They are all important, but I'm just being as I said in the beginning, I'm not expecting EW to be a big player, but these analyses are very important, so I'm including them on my channel. Agricultural benefits. EW applications with silicates improve agricultural production and soil health. Intensification of agricultural practices over time leads to soil degradation through acidification, depletion of plant essential micronutrients and macronutrients. This is just from intensification of agricultural practices. And also loss of soil organic matter and physical erosion that limits crop yields. Application of crushed silicates with EW could reverse these effects, as evidenced from multi-year large-scale EW field trials in the US Corn Belt with crushed basalt. So there is some evidence. Brazil has a long history of using various crushed silicate rocks in agricultural practices to improve soils and crop production and to facilitate the sustainability and autonomy of farmers, which strengthens the case for EW agricultural benefits. So how much more do I have? I have quite a bit, so maybe I should split this into. So just remember that there is the idea of CDR, carbon dioxide removal with enhanced weathering. Then there are all these co-benefits. So when you do life cycle analysis, it's important to make sure you are sequestering additional CO2 by this approach, but also how do you account for these additional co-benefits? If you're reversing the impacts of agriculture on soil quality, soil carbon, crop yields, etc., should they also somehow be accounted for in the benefit of enhanced weathering when you do life cycle analysis? So we'll come back and try to read the rest of it because it's a bit long and I don't want to make this podcast. It's already 30 minutes, so it's a good point to break now and come back later. See you in the second part, okay?